Today's 23 days left until IB Diploma Program Math Paper 1. And please comment below if you have any questions or anything concerning mathematics that you would like me to clarify in my following videos. Any topic 1, 2, 3, 4, 5 that is unclear, maybe some particular theme, something about integrals, something about derivatives, something about probability theory. Whatever you comment, I will try to accommodate and make videos in the future. Thank you. And don't forget to join the daily live sessions, also link in the description below, where we can actually interact. You can ask me questions and I can answer them, and they're practically free, so see you there. Okay, welcome to IB Math Prep. So in this video I'm going to analyze this exercise, which is a typical paper 1 exercise of topic 5. This has been taken, I think, from a high-level mathematics exam, but this video should be beneficial to anybody studying standard level mathematics or AI mathematics, both standard and high level, because I'm going to split basically this exercise into small parts, and I'm going to deconstruct it and analyze all the concepts in a way that should be beneficial to everybody. So in this exercise, we're given a function, square root of 1 plus x, and we are told that it's defined when x is greater than minus 1. Now, this exercise is about differentiation and induction, as we can see, and one thing we can immediately kind of ask ourselves is, why is x assumed to be greater than minus 1? Now, we know that square root of x is supposed to be the inverse function of the squaring function, meaning when we take the square of the square root, we get x back, and vice versa. If we square x and then we take a square root, we get x back. Now, this works when x is not negative, so greater or equal to 0. And this is because if I now just draw, if I just draw a parabola over here, which is the squaring function. Okay, here we go. It's a parabola. It's coming along. Here we go. And the parabola does not have, this squaring function does not have an inverse function, because inverse functions a function can only have inverse functions when it's an injective function. This is not an injective function because there are different points where this function attains the exact same value. So this is the reason why we always write plus minus square root something, is because there are actually two different functions and each of them has their own inverse. So the negative part of this curve and the positive part of this curve. So if I now remove the negative part of this curve just like this, then I'm left with this positive part, which is monotonic, and it has an inverse, and you always obtain the inverse by mirroring the function around this y equals x straight line. So here is how we get the inverse function, and so it's basically a parabola which has been shifted like this, tilted like this, and so this is the square root function, obviously, because it's the inverse of the squaring function. And we can see from this picture that also the derivatives, so the tangents to these functions, will be mirrored. In particular, when the parabola has tangent, the horizontal tangent at the very lowest point, so it's the derivative equals to 0 point, and you mirror it around this diagonal line, you get a vertical line, and vertical line is not a valid derivative. So if a tangent to a point in a curve is vertical, then the derivative would be kind of infinite or minus infinite. We don't treat it as a valid derivative, which which means that square root function is not, its derivative is not defined at 0, even though the function itself is defined at 0. And when this is the case, we often tend to define the domain of the function to exclude those points where the derivative does not exist. And in this exercise, it's very natural because it's all about derivative. And so when we plug in 1 plus x into the square root, then basically when is it greater than 0, and this time strictly greater so that it's differentiable? Well, exactly when x is greater than -1. So this explains why they have this condition over there. Now, I'm not recommending spending so much time during the exam to like prove this like I just did, that this is the exact correct way. But if you don't have an idea why, you should probably like think about it for a second, because it probably helps you to understand the exercise as a whole, and it will probably help you to get better intuition of what you're about to do. Okay, so let's move on to the first part, part A of this exercise. Here we are asked to basically just take the double derivative, so the second derivative of this function. And so we're faced with the problem of taking the derivative of the square root. Let me still just write it like this without the 1 plus, because I'm just curious about whether we know how to take the derivative. This is not directly given in the formula booklet as far as I can tell, but in the formula booklet we do have, one second, I'm just gonna bring up the formula booklet for myself. So here's the formula booklet. Let's scroll to calculus here. So here we have this rule that the derivative of x to the power n equals n times x to the power n minus 1. This is a very classic derivative rule, and the way it's written here suggests that this n must be an integer or a natural number, because they use the letter n. But actually this rule works for any rational n, irrational n. It could be even like x to the power pi. Then the derivative would be pi times x to the power pi minus 1. Why not? And so this rule helps us to take the derivative of square root, because we know that square root actually is the same thing as x to the power half. How do you know this? Well, we know this because as we already mentioned, square root is the inverse of squaring something. So x square root, the second power is supposed to be x. But on the other hand, if we take x to the power half and we square that, then using the multiplicative rule of the powers, we get that this is equal to x power 1, x to power 1, which is x, which is exactly the same thing. And because it's exactly the same thing, we realize that these things are equal, and canceling the second powers, we realize that square root of x is x to the power half. So this is how you get it. I hope this is not too small for you guys, but I already said what I wrote, so you must have understood what I did. Okay. Fine. So square root of x is the same thing as x to the power half. So let's just use our rule of taking the derivatives of x to the power something thing, and so the exponent simply jumps down and we subtract 1 from it, which means that we get half times x to the power 3, half minus 1 is minus half. Very good. Okay, So that's what will happen if we take the derivative of square root. Now, in our case, we actually have something inside of the square root. It's 1 plus x, and so we should be using the chain rule. So what happens when we try to take a derivative of a function which is inside of a function, or I mean function which has another function inside of it? So let's see, here we have the chain rule. Chain rule is today used a lot in machine learning. So if you ever wanna understand how neural networks work, you have to not only understand the chain rule in this form, but you have to understand the multi-dimensional chain rule, which is beyond our present video. Instead, we're looking at one variable functions, where if you take one function and take another function inside of that function, and then you take a derivative, it's the same thing as multiplying the derivatives. So taking the derivative of the outer function and then multiplying that by the derivative of an inner function. If you want a separate video about the chain rule, please comment below, because I could do a very long video about it, just about the simple stuff, not about the neural networks. I could do a video about that as well, because I was teaching a course about mathematical foundations of machine learning last year, but now we're teaching IB mathematics, right? So chain rule in applied to this case is simply, one second, is simply okay, so what is our u? So our u is 1 plus x, so our function is square root of u. So we first take the derivative of square root with u inside of it, so we just did it, so that would be like half, and then u to the power minus half, and then we remember that u was actually something, which is 1 plus x, and so this this has to be multiplied by the derivative of u, like this. Okay, but the derivative of this function 1 plus x is just 1, because derivative of 1 is 0 and derivative of x is 1. So it's just 1, so it doesn't matter. So the answer is simply this. Now, okay, this is we took the derivative of this function once. Let's bring our result back where it belongs. So there and here. Oh, very nice. Now, in this exercise, we're asked to take the second derivative, so which means that we take the derivative of the derivative. So derivative of derivative in this case is the derivative of this. And by this I mean this, oh my god. Wait a second. Okay, I lost my cursor. Here's my cursor. So derivative, oh, I'm sorry. Once again, let's fix this. I had the wrong thing here. So this is supposed to be 1 plus x. So the derivative of square root of 1 plus x equals this. Very good. Now, in order to take the second derivative of this, we need to take the derivative of the derivative, so the derivative of this. Good. Let's see how we are going to do that. So the derivative of this. Okay, now the constant, we gotta take it out from the derivative, and now we can apply the same rule as before, which is here, and this means that this exponent jumps down, it becomes minus half at times 1 plus x, and then minus half minus 1, which is minus 1/4 times 1 plus x, and then power minus 3/2. This is the answer. This is the second derivative of this function. So let me bring this solution upwards. I'm going to do it like this. Very nice. There it is. Okay. And but, well, it doesn't look like it's in the same form, because we were supposed to show that it is of this form, but now it's of this form. So how are we going to reconcile that? Now, there's another thing we have to keep in mind here, and it is that if you have x to some negative power, or like anything to some negative power, then it's the same thing as 1 divided by x to the same but positive power. Why? Well, because if you have 1 divided by something, then by definition it means that when you multiply it back to this x to the power a, then you get 1. On the other hand, if you have x to the power minus a and you multiply it by x to the power a, you get, by the rules of the exponentiation stuff, you get that this is equal to x to the power minus a plus a, which is x to the power 0, and that is always equal to 1. X to the power 0, always 1. Even 0 to the power 0 is 1. Okay, and so that means that this is the same thing as this. And now this means that these are the same thing. And so cancel this term, and you get that 1 over x to the power a is equal to x to the power minus a. Ta-da! This is the proof of that statement. But the reason I think it's important for you guys is because if you know how to derive these things, then you remember them better. And you need to remember them at the exam. Okay, very good. So this is this. And using this rule, we basically realize that our thing equals, okay, minus 1/4 times 1 over 1 plus x to power 3/2. And then, because we need to bring it into the form where there is a square root, well, we have already a half here in the exponent, and remember that something to power half is the same thing as square root, so we just need to transform this into the form of having a half in the exponent. So it's like 1/4 times 1 over 1 plus x, and now listen to this, power 3, and then this to power half. Now we know that this is how powers work. This is the same thing. 3 times half is 3 divided by 2. And now this outer thing actually is the same as a square root, so we can combine everything like this, and to power 3. Okay, there we go. Okay, now I'm actually going to leave this. Now we solved the first part of the exercise, but for the next part of the exercise, I'm going to leave this original form without the square root, but with the power minus 3 divided by 2, because you will see why. Because I cheated. I already looked at the exercise before making the video. I was thinking that at some point I'm gonna make videos where I just look at the exercises without ever seeing them before, because that's how you get best, you get to see how I'm thinking. But the downside of that is the video might become very boring, because I like, I'm just thinking. But sometimes it can be fun. All right. So next part of the exercise. Here we're asked to prove something like this by induction. Can look a little bit intimidating, but if you know what's induction, induction is when you prove something for an infinite amount of numbers by proving that it holds for one number, like let's say in this case is going to be 2, so it holds for 2, and then you prove another statement which says that if it holds for some number, then it always holds for the next number. And so then, because you already proved that it holds for 2, then by this rule, which you also proved that it whenever it holds for some number, it always works for the next number, it works also for 3. And because it works for 3 and it always works for the next number, it works for 4, and because it works for 4 and it always works for the next number, it works for 5, and because it works for 5 and it always works for and so on and so forth, it works for all numbers. By the way, induction itself is impossible to prove. Now, because induction is actually an axiom, it's impossible to prove induction itself. The principle of induction itself, you cannot prove. But you can prove other stuff using induction. Induction is a mathematical axiom. And this is something that goes completely beyond IB syllabus. So please don't think about that until the exams are over. And after that, feel free to Google Peano arithmetic or axiomatization of Peano arithmetic, and you will find a lot of stuff about mathematical logic and induction and definability, whatnot. But now this is completely beyond our present topic. So, and now, what are we going to do? So induction. Base case is when you do the first step. So you prove that your statement holds for the first number. Okay, in this case, number 2. So let's show that our statement holds for number 2. For this, we need to plug in number 2 into this pretty equation, and when we do that, we get that, okay, let's say 1 n minus 1 when n equals 2. Remember, n equals 2. So then this is just 1, so it's nothing, times 2 times 2 minus 3, 4 minus 3, that's 1 factorial, divided by n minus 2, 2 minus 2, 0 factorial. Okay, let's not be intimidated by 0 factorial just yet. Times 1 plus x to power half minus 2. Okay, and we're supposed to prove that this is equal to the second derivative. So when we have a number in brackets like this, it means that it's the nth derivative. So in this case, second derivative. Second derivative is the same thing as this thing, so these are the same thing. But if you want to like write the 42nd derivative instead of writing 42 of these apostrophes, which is a bad idea, you could instead just write 42 in there. And that's especially useful when your number of derivatives is n, like here. So you cannot even know what it is exactly because it could be any number. Okay, so we are supposed to show that this is the second derivative, but we just computed the second derivative here. By the way, I forgot to put this, that this is the second already. The second derivative is here. So now we only need to show that this thing here, oh my god, sorry. This thing here is the same as this thing here. But look, we already have everything is matching really, because let's see, so minus 1/4 to power 1 is just minus 1/4. Then this term here is 1 plus x to power half minus 2 is the same thing as minus 3 halves. Really the same thing, just calculated with whatever. Now we need to show that this thing equals 1, and now we have to face the factorial. Now the factorial is not as horrible as you might think. I love factorial. So factorial of n is just the product of all numbers from 1 to n. That's what it is. It's just as simple as that. Until n. This is factorial. It has the property that if I take the factorial of n and I multiply it by the next number, then as you can imagine, because the factorial of n is the product of all numbers until n, and then we just get, and then we add one more number, is the same thing as the factorial of n plus 1. And because of this, imagine what will happen if I have 0 here and 0 plus 1 here. Now I wanted to I'm sorry, 0 plus 1, just like this. So I wanted to satisfy this formula. But if I wanted to satisfy this formula, then this must be the same thing as factorial of 1. But factorial of 1 is the product of all numbers from 1 to 1, which is just 1. So this must be 1. Okay. So, but this is also 1. So what we have? We have the factorial of 0 times 1 equals 1, which very simply implies that factorial of 0 must be equal to 1. Now, obviously, I assumed here that I want it to satisfy this equation, which was deduced from something else. But that's a convention. That's how the factorial of 0 is always defined. I've never seen any exceptions to that, including our case today. This is just 1 divided by 1. Okay, let's move on. So we have proved the base case, because now we showed that this is the same thing, because we already showed that is the same as this. Okay. So instead of leaving all that mess here, in fact, even this mess I'm going to remove, and this mess I'm only going to take this, put it here, and then I'm going to say check, we did it. Then the next thing is to define the induction hypothesis. Now the induction hypothesis is that somehow this kth derivative equals to this formula, but a version where we substitute k instead of n. Okay, here we go. This is the induction hypothesis, so I assume this actually is true, and we actually know it's true when k equals 2, so all we need to do now is to prove the induction step, meaning from assuming this to prove that the k plus first derivative is this, but with k plus 1 substituted in place of n in this equation. Let me write that now. Okay, so here we are, and now we want to prove what? We want to prove that when we take the derivative of this, then we get this. That's all we need to prove, because this is the derivative of this, and if we know that this equals this, then we know that if we take the derivative of this, okay, this, and we get this, then we're done. Okay, so let's see what will happen if we take the derivative of this first thing. The constant is going to be unchanged, so let me just copy it from here. And then applying our rule, we take the derivative of this term. The exponent jumps down, and then the exponent from the exponent we subtract 1. So then we get half minus k times 1 plus x to power half minus k plus 1. Okay, how do we show that this thing equals this thing? Here's how. We will, that's my first idea anyway, but I did it and it turned out to be alright. So now I'm going to show you. This will be simplified with the intention to dig out these factors. And when we have dug out these factors from here, we will be left with a leftover term. And so we'll need to show that this leftover term is just equal to this. And notice that these exponents already match. Oh, I made a mistake somewhere. There has to be a plus here. I'm sorry. So we see like these exponents are the same. It's just a matter of brackets, right? So we just open these brackets. If we open these brackets over, oh my god, I'm sorry. If we open these brackets over here, then it looks exactly like this. So this part is the same, and if we only show that once we modify this into this form, the only leftover term will be equivalent to this, then we're done, right? Okay, so let's look at all these terms one by one. First, let's start with this. This term here is minus 1/4 power k plus 1 minus 1. On purpose, I didn't simplify it. I don't have to. So minus 1/4 to power k plus 1 minus 1 is the same thing as minus 1/4 times minus 1/4 to power k minus 1. What did I do? My purpose is to dig out from here these terms. And so if I want to dig out this minus 1/4 to power k minus 1 from here, what I do is that I take one of these factors out, so to speak. So this is the factor I took out, and I'm left with this factor, which is exactly this, what I want. Next, let's move to the nominator here. The nominator there is 2k plus 1 minus 3 factorial. And if I want to dig out this term 2k minus 3, I'll have to use the factorial rule because this is the same thing as 2k minus 3 plus 2. Yeah, I opened the brackets and then I changed the order. And so using the factorial rule, which I have had before here on the screen, this is equal to 2k minus 3 factorial times 2k minus 3, plus 1, and 2k minus 3 plus 2. That's how you do, that's how you open factorial. And then the third term, which is k plus 1 minus 2 factorial, that is equal to k minus 2 factorial times k plus 1 minus 2. Okay, at this stage we can already simplify it. It's just k minus 2 factorial times k minus 1. Okay, so now I have all these terms converted to their original meaning, and so what I can do, I need more space, but let me just take this part, put it here. Actually, let me just remove this. So I'm looking at this term. Okay, I'm looking at this term, and using my 3 calculations over here, I can substitute them there in a way where I'm separating the extra terms from the original terms. So the original terms come first. There's going to be minus 1/4 to the power k minus 1 times 2k minus 3 factorial divided by k minus 2 factorial, and then now I'm gonna put all the extra terms which I got from here. I get minus 1/4 times 2. I'm just gonna copy paste from here. And resize. I need to resize it. Otherwise, it's okay. Does it make? Do you see it if I resize it? No, I'm not gonna resize it. So it's not gonna fit. 1 second. No, it's actually better that I just rewrite it, but I will simplify those terms because they're way too big. So the first term, this one, becomes 2k minus 2, and then the next one is just 2k minus 1, and then divided by k minus 1. So now we see that we were able to simplify our next term. So we were able to simplify this term so that it looks like this term but multiplied by something, and this something, if I can show that it's the same as this term over here, then I have basically shown that these are the same, which is exactly what I wanted to show. So how am I going to show that this complicated looking term is equal to half minus k? Very easy. I'm just going to realize that here I have 2 and 2, and if I take that 2 out, I get k minus 1, and so then these k minus 1s will cancel each other. So if I may, just to work with this term, this is going to be 2 times, okay, I'm going to include this, okay, I'm sorry. I'm going to work with this term, which is the extra term, minus 4 times, then 2, and then k minus 1, and then 2k minus 1, and then divided by k minus 1. Now these cancel. So, well, and these 2 makes this 4 into 2, so we have minus, and then 2k minus 1 divided by 2. Minus, so what we can do is that it's just 1 minus 2k divided by 2, and now we already see that this is simply half minus k, which is exactly the term here, which is why we're done. This proves the induction step, and yeah, that's it. We're done. Thank you for watching.